Welcome to session 8 in our series on electricity and magnetism. We're going to start with this apparatus right here, where we have a bunch of copper wire out of an extension cord. Both the white and the black do the same thing. They go around and around this little dowel here, and it's really a loop that's drooping or squashed, and we're going to run electricity through it. I'm going to place this magnet here just so that you will know that whatever is happening is a magnetic effect. So I want you to watch what the wires do. Okay, you ready? Here we go. All right, you saw that it was a magnetic effect. I'm going to remove this now. And you probably noticed this. But that was so graphic, you may have missed that these pulled together and these pulled together as they went out. So I'm going to turn this way so that that's clearer. And I will energize the circuit again and watch what these wires do. So they're pulling together. So how do we explain that behavior? These are going out. These are pulling together. Electrons are coming up one side, going down the other. It could be the other way around. It could come up this side and down the other. It doesn't matter. They're opposites here, and all the electrons are moving in the same direction when they pull together. And when they're in the opposite direction, they push apart. So how do we explain that? Well, the easiest way to do that is just to refer to our two left-hand rules. Let's assume that these two wooden dowels are electrical conductors, and we'll start with flowing electrons down this conductor. So our first left-hand rule tells us that if electrons are moving down the wire, as indicated by this red thumb, then the magnetic field will be in that direction around the wire. Now what that means is anywhere on this side of this wire is a magnetic field in that direction. Now, let's flow electrons in this wire. We'll start with the electrons moving downward. Our second left-hand rule tells us that if the electrons are moving downward, as indicated by the red thumb, through a magnetic field in that direction, they will experience a force in that direction. So these two wires will pull together. Now, if I reverse the flow in this wire, with the electrons moving up through a magnetic field in that direction, then the force on the wire will be in that direction, so the wires will push apart. Now, it doesn't matter which wire I started with, as with the first left-hand rule, and which one had the second left-hand rule, the results would be the same. And that's pretty much what you saw with this device. Electrons are traveling in opposite directions here as they are here, so it should push apart, and it does. And then now, these are all moving in the same direction, so they should pull together and these will pull together. Just like the two left-hand rules predicted. Watching this makes you think, well, maybe all that magnetism is it's just a movement of electrical charges. Makes sense. But if that's the case, what's going on in here with these magnets, the permanent magnets? What kind of electronic behavior is going on? There's no wires, there's no batteries. How do we explain this? Well, to understand that, we must look at the electronic behavior in the atom. Electrons have something called spin. They act like tiny gyroscopes, and associated with that spin is a magnetic moment. It has a magnetic field around it. They act like tiny little electromagnets. So an electron has mass, it has charge, a negative charge, and it acts like a tiny electronic electromagnet. Now, although atoms of all of the elements have these little electronic electromagnets, in most materials, the magnetic effects are negligible or non-existent. And that's because the magnetic fields of the electrons, the way they are fitted into these various energy levels of the elements, are always, they tend to cancel each other out due to certain rules of physics. Only in elements with certain electronic configurations are electronic magnets able to more freely interact with each other, align with each other, and maybe self-magnetize in regions that we call domains. This behavior is called ferromagnetism, and it's exemplified by elements like iron, nickel, cobalt, and also alloys, modern alloys that have just, they exhibit powerful magnetic behavior. So let's look at some diagrams of domains, and then we can discuss their behavior. So here is this is a typical drawing you might find on the internet in images for domains. And the arrows indicate the direction of the magnetic fields of all those little lined up electron spins. And in the next domain, they're in a completely different direction. Here they're pointing that way, here they're pointing that way, over here it's that way, here it's this way. So when you get away from this very, very far, the net magnetic field is zero. There is no real magnetic effect. Now, here's another. I'm going to take the same pattern of domains. This is a little bit more organized. In this case, the domains have interacted with each other to some degree, and so the north ends of this one are adjacent to the south end of this one. The north end of this one is adjacent to the south end of that one. So it's kind of head, tail, head, tail, head, tail, and it's even more self-contained. So all of the magnetic field is inside here, and there's no magnetic field out here. Now let's take a simple case of domains. And we've got 7 domains here. 1, 2, 3, 4, 5, 6, 7. And you'll notice that here's, of these 4 representing the spins that are pointed that way, there's 2 going that way, 2 going that way, and then they just come around. And so it's, again, very self-contained, no magnetic field out here. Now if we place this, let's say in a coil of wire, okay, and it's set up so that when I turn on the electricity to the coil, we produce a magnetic field that way, then this domain will get bigger because the electron spins adjacent to this domain will flip. And so this will get bigger, these will get smaller, these will get smaller, and we'll have a situation like that. Now, notice that there's a lot more spins pointing that way than there are pointing that way. So this is now magnetized. There is a magnetic field out here. If we were to turn the magnetic field off, in some materials like softer steels, they would go back to a situation where the magnetic field is self-contained again. In other materials, it might stay that way. Those we would call permanent magnets. If we really push this, really used a powerful external magnetic field, in that direction, we would reach something called saturation, where almost all of the spins are now pointing in that direction. All right, so what I want to do now is I want to model the behavior of the electrons. And what we're going to do is we're going to, instead of using electrons, which we can't see, but they are tiny magnets, okay? They're acting like tiny magnets. So we're going to use macro-sized magnets and large arrays and see if we can kind of duplicate some of that domain behavior, okay? All right. So here is an array of compasses. And let's move out a little bit. I know it looks a little foggy there because of the reflections of some of the lights I have. Now here's the problem. If I get rid of the reflection, you don't see the colors as well. So that's why I'm going to keep that on, because it's easier to see what the compasses are doing. Now, except for a couple of stragglers, these compasses are pointing where they should be, which is that way. This is north. This is north in my shop. In my area where I live, do I have a magnet there? Let's do that one more time. Here we go. There, that's, well, I've got a couple of stragglers. Okay, so they're mostly pointing the way they should. The red end is pointing that way. Here, let me line it up with the north arrow here. That's good. Now I'm going to rotate this. And as I do, you will notice most of them stayed lined up that way. Most of them stayed the way they were, even though this is north. Most of them stayed that way. Why? Why aren't they lining up with the Earth's magnetic field? Well, the reason is, once they were lined up where the north and the south of these two compasses and these two were close together, they were perfectly happy to stay that way. They're more attracted to each other. That force is stronger than the Earth's magnetic field is for them. So they're staying the way they want to be. Now I'm going to stir that up real quick, and we'll take a look at what happens. And it looks like chaos to us, but remember, these are little magnets. Compass needles do not necessarily point north or south. They respond to whatever the local magnetic field is. And for them, with their proximity to each other, they are interacting more strongly with each other than with the Earth's magnetic field in many cases here. So here we got them lined up with the norths this way, the norths are this way, here the norths are pointing this way, here they're pointing this way, here they're pointing that way. These are like miniature domains, okay? They interact with each other more strongly than with the Earth's magnetic field. Now we're going to do a similar thing, but with stronger magnets, because compass needles are very, very weak magnets. Now here is an array of magnets. I'm going to zoom in a little so you can see how this is made. These are little disc magnets, and they're just sitting on a little wooden, let's see, here, where can you get my finger there? Yeah, they're floating on little pins. It's a block of wood with a little disc magnet in the middle. And right now, they're not having any impact on this compass. Very little. Very little impact. Now, let's take a look at the way these are organized. Let's move this out of the way right now. And here we go. Okay. I'm going to look for some patterns. I've got two kinds of patterns I like to look for. One of them is this one here. This is really very typical. See the blues across from each other? They would normally repel, but they're not repelling because they're attracted to the reds right to the left and the right. And same with the reds. So the attraction is stronger for these than the repulsion. It's a low energy level. And here's another one. And let's see if we can find a couple more that are clear. Here's another one. And this is almost, but I don't want to claim it yet. Do I see any more here? Okay. I think I've oh, here, this isn't bad. This is kind of like that. All right. Now the other kind of magnetic, oh, I missed this one. And then we have this, south, north, south, north, south, north. So I have this kind of interaction and this kind of interaction, or you could make this a larger loop. They are interacting with each other. Let's make this one a longer loop. Okay, I missed that one. There's low energy level there. And this is like that. So you get the idea. We have these types of, these are like domains. Okay? They're working with each other. And we're not getting hardly any magnetic field over here by this compass. Obviously there's a little bit going on, but it's not much. Now we're going to magnetize this. Okay? So let's get our little table set up here. We're going to use these droopy loops to magnetize this array of magnets. Okay, that's pretty good. All right. So, now when I do this, I want you to notice I'm going to saturate it first, and then when I turn it off, they do their own thing and it goes away from saturation. Watch now. I'm going to do it. All the reds are pointing that way, all the blues are pointing this way. It's saturated. And now they did their thing, but it is far more polarized than it was before I put it up there. And you can see that by noticing the compass needle here, okay? Much more responsive than it was before. And that's because if you look, even though it looks like they're which away, the reds are pointing somewhere in that 180 degrees, and the blues are pointing somewhere in this 180 degrees. There are some that are almost that way, but none of the blues are pointing that way, and none of the reds are pointing that way. So we have magnetized this. Okay? All right. Let me demagnetize it. And now we're back to where we were when we first started. Obviously there's a little bit of magnetic effect, but it's not very strong. Okay? Now the last one I want to show you is this right here. I'm going to zoom in on this so you can see the pieces. Okay, so we've got 6 magnets. Oh, this is still magnetized. There we go. We have 6 magnets, and they're going in a circle. This domain is a circular domain. North, south, north, south, north, south, north, south, north, south. They're perfectly happy. The magnetic field doesn't go out much farther than that. Watch the compass needle. Whoops, sorry. Let's get out here where you can see the compass needle. Okay, so very little effect. I'm getting pretty close there. Get close enough, the single magnet will affect it. These are not weak magnets. This is these are magnets out of an electric toothbrush, the part you throw away. You may want to salvage those for a variety of reasons. They shouldn't go into solid waste anyway. But this little magnet is holding a 2.5 pound piece of steel. That's how strong that tiny little magnet is. But right now, it's not doing anything out there. It's not hardly affecting the needle at all. So let's magnetize it. We'll put it in here. And this doesn't require the amperage that the other one did. Okay. Now, I guess it's good enough. So you'll notice I'm not even over here now. We've got quite a magnetic effect. So we have magnetized these guys. All the reds are pointing that way. All the blues are pointing that way. Even from this distance, I can affect that needle. And if we stir them up, they'll go back to their happy domain space with no magnetic field there. So right now we went back to demagnetize. Well, I hope you've enjoyed this session and you've learned a little more about how domains work in ferromagnetic materials. In the next session, we are going to take a look at these soft steel type of ferromagnetic materials and learn about why they're so important in our electrical world and why we use them for our motors, our generators, our transformers, nearly all of our electromagnets. So thanks for coming. I'll see you next time. Take care.